Hello everyone, welcome to this session of Spectral Geometry in the Cloud. It's a pleasure to have José Espinar from Granada. He will talk about an overdetermined eigenvalue problem in S2 and the critical catenoid conjecture. José, the floor is yours, and we will have a look in chat if there is any question.
Okay, thank you. Thank you very much for the invitation. And today I would like to talk about one problem and relate with a big problem now in minimal surface, that is the critical catenoid conjecture. So the talk today is going to be based on a paper with my former student Diego Marin. The idea is to relate solutions to this eigenvalue overdetermined problem, this one. So consider a domain in the sphere that supports a solution, a positive solution in the interior to this eigenvalue equation. There is zero at the boundary, and the Newman condition is constant. Then we are going to relate this solution to this problem with minimal surface in the ball, in the Euclidean space. So what we're going to do is to classify annular solution to this problem and then translate that to the critical catenoid conjecture. So first, let's start with overdetermined problem, and that this is an old topic in physics and mathematics. The idea is the following. Suppose that you have a Riemannian manifold and you take some kind of domain, about the domain at the beginning, okay? And you take some Lipschitz function. So try to solve this problem is always possible, right? You have in the interior some kind of elliptic equation with Dirichlet condition at the boundary, so you can always solve this kind of problem. But if you assume also that along the boundary you have some kind of Newman condition, this problem becomes overdetermined. And in general, this problem might not have solution. And what is likely to happen is that when it does have a solution, the solution will determine the shape of the domain, not only the solution, but also the shape of the domain. You cannot find solution to this problem, the whole problem, in a domain that you want. So the question that arises is that, what can we say about the geometry? Suppose that you have an overdetermined problem in some body domain. Let's start in the Euclidean space, okay? What can you say about the geometry of this domain? So the first result that we know, the most famous probably, is the Serrin theorem, okay? Serrin consider the equation when the f that I consider the beginning is equal to 1. This is the equation, that is the Serrin equation, okay? So he proved that when you have a bounded domain in the Euclidean space, so that support an overdetermined solution to this equation, which is 0 at the boundary, and the Newman data is also constant, then the domain has to be a metric ball. Then the solution has to be a readily symmetric solution. So at the beginning, I assume also the solution that we were looking for were positive. In this case, the positivity in the interior is clear by the maximum principle, okay, and the shape of the equation. So, but this theorem is very important, but for me, the most important is the technique that was introduced. And the thing that Serrin, what he did is to extend or translate the moving plane method created by Alexandrov to the realm of elliptic equation. So Alexandrov proved in the 50s that any embedded CMC, closed surface have to be a sphere. And the way he did it was using moving plane. So he took a plane far away from your compact surface that did not touch him, then approach the plane until the first contact point and start to do reflection until you find a plane of symmetry. So he can do that in any direction. Then the conclusion is that your surface that you starting with is a sphere. So that method was implemented by Serrin in the realm of this kind of equation. But the very same year that Serrin proved this theorem, Weinberger also proved the same result, but using what is called now the P function. What he did is the following. Suppose that you have a solution to this equation, then he was able to construct a P function this guy here, in terms of the solution, says that it's subharmonic in your domain. Then he was able to prove that the domain have to be a ball if and only if this guy is constant. And the constancy of this is a chain showing that this guy has an interior maximum. Okay, that's the whole idea. So in order to prove this theorem here, that solution, when you have an overdetermined solution in a bounded domain of this equation in the Euclidean space, you have two different ways of proving that using, say, geometrical method, using the moving plane method, or more analytic method using the P function, okay? So the moving plane method was generalized by Sorin and Pucci for general equation, not only when f equal to 1, but the only condition that they need is that the f is a Lipschitz function, okay? So the thing is that they prove it for equation of this type, this here, right? U plus f of u equal to 0. With this f here is Lipschitz, this is enough to use the maximum principle. That is what you really need in order to prove, to extend the moving plane method. This is for the Euclidean space, this one, this is for Rm, and then in other space form were extended or generalized by Kumaresan and Prajapat. In the hyperbolic space, it's exactly the same than in the Euclidean space, exactly the same, but in the sphere, they were able to extend the result when the domain is contained in a hemisphere. And the reason is the following, okay? Because even in the sphere, we cannot use the whole power of the moving plane method, because we need, in order to use the moving plane method, to ensure that you have a plane that doesn't touch your domain, okay? So in the case that your domain is in a hemisphere, this is the case, right? So now the plane that you are going to do reflection are, say, equators, okay, in this picture here. So if the domain is contained in a hemisphere, you are in a situation like this. So you are going to take, say, this geodesic here, and then you are going to start to rotate over this axis, like in this picture, you are going to start, and then you can find for sure one geodesic here that is going to touch for the first time, and then continue to do the moving plane method, the reflection, and then you are going to end up in this situation having a plane of symmetry, but in this situation in the sphere. So in the sphere, you cannot have the same result in the whole sphere using this method, because you might have domain like Clifford torides in some sense. Okay, that is a equidistant from an equator that doesn't satisfy this condition that I said. So, but this result was in the 90s, this was in the 70s, but in the last decade, many people in geometry got the attention to this kind of overdetermined problem, because the theory of CMC and minimal surface, many things in common with this problem. And in particular, my attention came when I saw some result by Pier Alberto, Sivaldi, Antonio, and David Ruiz, okay, where they study about the domain in the space form, say the Euclidean space, and they use ideas that come from the theory of properly embedded CMC surface in the Euclidean space. So when I saw that the relation, I tried to think what happened in the hyperbolic space. So we extend this result in the Euclidean space to the hyperbolic space with Jim Mao and Farina Masset. What we did is try to use the theory of CMC hypersurface in the hyperbolic space to get result for unbounded domains for this kind of equation in the hyperbolic space. Then what happened in the sphere? In the sphere, I say that you can, using the result here, you can classify domains if you know that such domain is in a hemisphere. However, it's known for minimal surface in S3 that if you fix the topology, that for a minimal surface has to be a topological sphere, have to be an equator. So that's based on the index method, okay? It's the Agram result. What we did is to extend this index method with Masset for bounded domains that are topologically this in the sphere. So you don't need using that assuming that the domain is simply connected, you don't need to assume that it's contained in a hemisphere, okay? And this comes from the idea here is the also well-known Hopf theorem in R3, okay? Hopf theorem say that if you have a topological sphere with constant mean curvature, have to be a round sphere. You remove the embeddedness in the Alexander theorem, and you replace embeddedness by a topological condition that is a round, is a topological sphere. Okay, this is what we use here. And also, talking about P function, is that in the Euclidean space, you can extend that method for other divergent forms equation. This was done by Garofalo and Lewis, or for some product manifold by Farina and Corel. So geometric method and P function method has some advantage and disadvantage. The advantage here is that the equation is very general. You don't need to control a lot of the equation. You only need that the equation satisfies the maximum principle. Here, you need to control the equation. You need to control the equation because you need to construct the P function, and the P function depends on the equation. That's one thing that. But here you need, for example, you don't need in this that the domain fix on topological condition of the domain or that is contains some hemisphere or whatever. So it has more flexibility on the behavior of the domain. Here you have more flexibility in the behavior of the domain, but less flexibility on the equation. And here is the opposite. So both methods are good depending what you want to do, okay? And in this talk, we are going to use both methods because we need both methods. But the thing is that it's not true in general that we always, if we have a overdetermined solution in some domain, it's always going to be like symmetric or so on, okay? The first example in that sense was done by Delay and Sivali in 2013, where they construct a solution to the first eigenvalue of the Laplacian in general compact manifold that are not rotational, are not symmetric in some sense, okay? And also, if we don't assume that the solution is positive, so David Ruiz recently showed that even in the Euclidean space, if you choose the function f properly, okay, you can find domains that are not bold, where you can find solution to the overdetermined problem with solution to this elliptic equation in the interior. Okay, so in some sense, you need all conditions in order to ensure that if you have some solution in your overdetermined problem, then you will find some kind of symmetry of your solution and the domain and so on. So one thing important in the result of the ring is that in the case of the ring, I say there is a bounded domain, but I don't say that only have one boundary component, right? I don't say it's simply connected. You may have some kind of domain, say with 3 boundary components, right? And this is interior, this is your domain. But one thing that we do ask in the ring case is that the Newman condition is the same 3 boundary. Okay, that's very important. Here you can apply the Alexander reflection method or the ring method right now. But what happens if I say, okay, suppose that to find domains like annular domains, and I'm going to assume that the Newman condition here is one thing, and in the interior is another constant. Okay, what can I say about those kind of equations? So the first thing is that it's clear that I can construct even rotationally symmetric solution, and the idea to construct solution to this equation in an annular domain is this is the solution in the ball, and this is the green function of the Laplacian. Okay, that is given depending on the dimension is given by this expression. So if I arrange the constant properly, I can find solutions that are going to behave, and then you have to do the rotation of this about this x-axis. Okay, these are the solutions more or less of this equation. So can we classify those kind of rotationally symmetric solutions that are not in a simply connected domain, but in an annular domain? So this is what we want to do. But one thing for sure is that if we want to classify those solutions, for sure we need to ask different Newman conditions in each boundary component. Okay. So now we're going to assume that I have a domain, say in the Euclidean space, okay, with at least two boundary components. Say, for simplicities, assume that it's two, okay? And I'm going to assume that the Newman condition is locally constant, implies that the gradient is constant along each boundary component, but probably different constant. So in this situation, the first result that we know is this one due by Rechel or Sirakov. That this is not exactly the same problem that we have, because the condition that they put is that in one boundary condition you have a Dirichlet is 0, say it is 1, and the other is a positive constant, is here, and then the Newman data is not necessarily constant, but is less or equal than 0. It means that the solution, the graph of the solution, is something like this. In this situation, you can also apply the moving plane method to prove that actually this annular region have to be rotationally symmetric. Okay, this is the result. But if we want to assume, if we want to classify solution now to this problem, say for the simple problem of the ring, but in annular domain, okay, so in some kind of annular domain with one boundary Newman condition here and the other condition here have to be different. Oops, sorry. C2C1. So there is a very interesting paper that has been published recently in the Journal of the European Mathematical Society by Virginia, Lorenzo, and Stefano, that they classify, they have two theorems. They have a classification result for this kind of solution and an existence result. So, and the theorems are the following. The first one is the classification that say that if you have a solution to this overdetermined problem in the Euclidean space, in the Euclidean plane, and the solution, that's a very important condition, has an infinite many maximum, okay, then it has to be rotationally symmetric. So recall that that's what's happened. The solution, right? We're here, right? Here, this is the maximum, and you have a curve of maximum. So you have an infinite number. So, okay, this is the first result. That this is the one that we are going to extend in our situation that I'm going to tell in a few minutes. And the second is that actually non-rotationally symmetric solution to this problem, okay, in annular domains. So the thing is that you can do a bifurcation argument and find a solution to this problem in an annular domain that is not rotationally symmetric. The thing is that this solution has only a finite number of maximum, okay? So you have this dichotomy. So the thing is that our situation that we're going to see in a few minutes is going to be in the sphere, and we can translate, or we can extend this result with this condition, but I cannot do that, this one, okay? And I would love to see the extension of this one to my situation, because, and then if you are careful, or I will explain at the end probably, so if you are able to have a theorem like this in the situation that I'm going to explain in the sphere, so you will be able to disprove the critical Catenoid conjecture. So it's a problem that is worth it to look. Okay, so the idea that we're going to discuss today comes from this part of the paper. So with the situation, or the equation that we are going to study, I want to study this eigenvalue equation. Okay, I take a domain in the sphere in S2. Okay, and I'm going to assume that I have a solution to to this eigenvalue problem that is positive in the interior, 0 along the boundary, and is locally constant. Probably in each boundary component might be different. For simplicity, so assume that is an annulus. You only have 2 boundary components, okay? Because it's the one that I'm going to really focus. So, okay, this is the objective that we have, classify the solution. In order to classify, I need the condition that I explained from the paper of Agostiniani, Mattieri, Borghini, that is going to have an infinite number of maximum points, okay? So the difficulty here is that I cannot use, or we cannot, it's not clear how to use the moving plane method, because annular region most likely it's going to be like you are going to you cannot put them in a hemisphere. Otherwise, I can use the moving plane method, like so. But most likely, you are not going to. So the situation, more or less, is going to be, imagine that I have the sphere here. What I'm going to have is a domain. Oops, it's a domain here. So imagine like it's a Clifford Choroid, something like that, like the image of the Clifford Choroid. So it's going to be something like that. So I can start the moving plane method. And also another observation, as I say, is that this equation, we can have a P function, okay? But P functions are good in order to classify simply connected domains, okay? Bonds, not in this situation. So, but we are going to use it in order to control the topology of our domain, okay? So this is an observation. This is a simple computation from the equation. It's not complicated. And at the end, we are going to use all the method that I say. Okay, and the result is the following. So, okay. Okay. So suppose that you have a solution, okay, of this equation in some domain that is of the topology of an annulus, okay, so that has 0 Dirichlet condition along the both boundary. The Newman condition is constant along each boundary component, and the solution has an infinite number of maximum points, okay? Then this guy have to be rotationally symmetric and actually have to be a set of points or have to be symmetric with respect to some axis perpendicular to the plane defining this equator. So the idea is the following. So you have, say here is the equator, and then your domain is going to be like a band with respect to that equator there, okay? Those are the domain that we're going to look for. And the first observation is the following, and that's it's important. Suppose that I have a solution of this, and I have an infinite number of maximum points. So the solution to this equation are analytic, okay? Always are C2, and C2 implies analyticity. Then the level set are analytic, so the set of maximum are analytic. So you have an infinite number in particular that tell you that at least you have a curve of maximum. Let's say this one. So if you assume that it's ring shape, the only possibility is that you have one curve and probably isolated points in the interior, okay? That's the only possibility. You cannot have more possibilities. Why? Because what are the other possibilities? The other possibilities is, so for sure you have a curve. This curve be contractible in your domain, because otherwise you create some domain in the interior so that the boundary is maximum. Then you have a positive minimum in the interior, which is not allowed by the maximum principle with this equation. Then you cannot have any crossing of this maximum, because at this point the Hessian have to be 0. But the Hessian 0 implies that this guy is 0, but this is positive. It's not possible, okay? You cannot have this situation. Or you cannot have 2 curves that a domain, right? Like this, because this situation, you will have a domain, like in this situation, and you have a contradiction with the maximum principle. So all these cases are not allowed. And the only possibility is when you have an infinite number of maximum points is that you have a curve of maximum, that is not going to be contractible in your domain, and a finite number of isolated maxima. This is the situation that you have to be in mind, because this curve is going to separate the annular region into two domains, right? Like this one and this one. And what we are going to do is to compare this sub-annulus with the model annulus, okay? That's the whole idea. Okay, so the sketch of the proof. So the first thing is that I'm going to describe explicitly the one parameter family of rotationally symmetric solutions that are of annular type, okay? Like the previous one I showed you for the serine equation, but for this kind of equation, okay, in the sphere. So there is a one parameter family. We can parameterize them by one parameter. And then what I'm going to do is like take one of these sub-annulus that I told you before, okay? And then I'm going to give an explicit relation. I'm going to, given that domain, I'm going to construct, I'm going to give a rotationally symmetric solution associated to my domain and a solution, okay? And then what I'm going to do is to compare the level set of both, okay? I'm going to compare the level set of this guy with, say, a function, a properly constructed function, with the level set of the model solution. That allows me to compare the geometry of the level set, okay, of my original solution. Okay, this is more or less the idea. Okay, I'm going to take the maximum, I'm going to take a sub-annulus, and this sub-annulus, I'm going to relate with a specific model solution that is rotationally symmetric, okay? And I'm going to compare the level set of both. But that, using that construction, is going to construct that relationship. Then I'm going to compare the gradients, and that gradient will give me information about the curvature and the length of the level set on my original solution. And that is going to be enough in order to conclude rotational symmetry, because this curvature and length estimate will allow me to say that one of the components, say this one, or the complement of this one, is contained in a hemisphere. And then I can use the moving plane method to conclude that it's rotational symmetric, and since it's analytic, everything has to be rotational symmetric. So the first thing is to construct the one parameter family of model solution, okay? So the way to do it, or the way that we do it, is the following. Take the equation, I'm going to consider cylindrical coordinates, and I'm going to consider rotationally symmetric solution with respect to this coordinate, to this equation. Then you can compute explicitly the solution, because it's an ODE, okay? And this solution are defined by explicitly this equation. And you have two parameters, okay? This omega and this alpha. And we are going to parameterize by the height where is the maximum of the solution, okay? This R is where is the maximum of the solution, okay? I'm going to explain at the end how to relate these parameters. These are right now analytic parameters, but from the point of view of the geometry are very clear what they are. And the idea to construct this solution are the same that Agostiniani used, is that you take the solution in the ball, in the simply connected domain, that is this part here, and the green function. And the green function is this part here. And then you sum both of them. And you observe that this equation is a scale invariant. So this is this parameter here is the scale parameter that is not very important, but we are going to fix in some way, given by this expression. There is when explain the geometric part of this correspondent, you will see why I take this guy here. But the important point is that you can parameterize this solution only by where is located the maximum of the solution. Okay, and it's given by this expression that is explicit. And recall, this is the solution in the simply connected domain, and this is the green function. This part is the one that is coming from the Catenoid. Okay, so What are the behavior of the solution? This is the behavior of the solution. This is how you see, okay, you see here the sphere. This is the representation where the critical, the height, the R is 0. This is the symmetric solution, okay? You can see you have one boundary here, one boundary here, and this is the graph of the function, okay? This one here. And this is how behave the solution when the parameter R is going from 0. This is R equal to 0. There is the equator, is R equal to 0 is the symmetric solution. There is this one that is here, okay? And when I move R to 1, it means that the maximum going to the North Pole, this goes to the simply connected domain, okay? To the solution that is defined in a hemisphere. This is for R equal to 1 there. So you can parameterize explicitly everything in order, in terms of where is located the maximum, okay? This is R, okay? We call this R. This is the maximum, okay? And observe that this, I'm going to take this solution, for example, okay? So if I remove the curve of maximum, I have two sub-annulus. They say the minus and the plus, okay? This is the minus and this is the plus here. So now what I'm going to do is a unique way to differentiate between this part and this part.
Jose,
Yep.
can you explain again what happened when R goes to 1? You said that
Yeah.
it go. So what happened to the other boundary component?
Yeah, sure. Look, when R goes to 1, this boundary component here and this boundary component here is the one up here. So when R goes to 1, this boundary component collapses to the North Pole. The gradient, you see that goes to infinity.
Mm-hmm.
So
Okay.
the solution is the following. So you have the sphere. The maximum now are here, okay? And the solution, what you see is something like that. But here is the maximum. That is the solution. So these guys, when R, this is R, right?
Okay, yeah.
This is R the cylindrical coordinates, okay? This is R equal to 0, and this is R equal to 1. So R equal to 0, the solution is the symmetric one that is given by this one. So now when R goes to 1, so this component goes to the equator. This component here goes to the North Pole. And the solution collapses from an annulus to this.
Okay, thank you.
Okay, so now I need a way to distinguish those sub-annulus, right? I have the plus and the minus. And this is done using the stress function, okay? The stress function is nothing but, if you think in an overdetermined solution, it's like the quotient between the gradient at the boundary and the maximum, okay? That gives you a unique value, because observe what's happened in this example, right? In the rotationally symmetric. Okay, you have your maximum, it's the same. But here the gradient, okay, is approaching to 0, okay? You see that the gradient is every time more horizontal. So the gradient here is going to 0. And here is the opposite, it's going to plus infinity. Then what's happening in the model solution is that you have a stress function for the minus annulus and the plus annulus in the model solution. And the thing that when R, the critical, the height, the maximum value is at height 0, both are the same because it's symmetric with respect to that equator, and it's some value, is tau, is bigger than 1. And then you have a function in the plus annulus that goes from this value to plus infinity, and the other one goes from that value to minus from that value to 1. So it's decreasing. Okay. This says what happened. So I have a well-defined function, this tau, between 1 and plus infinity. Okay, but I have to distinguish if it's bigger or So the first thing that this is for the annular domain, the rotational symmetric annular domain, but I want to see, the first thing that I need to see is that this stress function in any domain that I take can distinguish the topology. And it does when this guy is less than 1. When the stress is less or equal than 1, one can prove that the domain has to be is simply connected, and then by the result that I have with Maset, have to be a hemisphere. And the idea to that is using the P function in one part, and it's the following. So suppose you have domain, and you have your set of maximum. You have two possibilities. I'm not assuming here that you have an infinite number, okay? So you have two possibilities. This set separates or doesn't separate. So if it doesn't separate, okay, so it implies that, for example, you have a finite number of maximum points, then this condition implies that this P function has interior maximum. And then, since this is two harmonic, implies they have to be constant, and then this implies rigidity, like in the case of Weinberger, okay? In the case of separate, it does separate. One thing that you prove first, that this condition, tau less or equal than 1, implies that this energy function of the level set is non-increasing. But then, this gives you a contradiction, because if it does separate, I can consider one of the components, and this term, when I approach to the set that goes to the maximum, this has to go to infinity. So this energy has to go to infinity. However, it's non-increasing. What it says that the E of t is less or equal than the value of the energy at the level 0. But at level 0 is fine, because we can compute it explicitly, this guy. So this is a contradiction. So this 3 point implies that if the stress is less or equal than 1, then it's going to give you that the topology of the domain have to be simply connected. Okay, it cannot be annulus. So that's good, because the radial annuli, the stress function is always bigger than 1. So there is a way to relate. So now we can define, using the above, the expected critical height. What is that? The critical height is where it should be the value where are the maximum of the solution. So take a solution, okay, of the Dirichlet problem, and take a component away from the maximum, okay? So take the domain minus the second maximum. I don't know if that domain is the whole thing or it's not. I'm not imposing that this guy, so far, for this definition, I don't need that this guy separates, okay? And the only thing that we are going to assume that is not a topological list, okay? If not a topological list, the stress have to be bigger than 1, for sure, by the previous theorem. Then, what I can say that, okay, if the stress is bigger than 1, but below 0, that is the one given by the symmetric solution in the radial model solution, I'm going to define this R by this equation that is well defined, because this is a differential. And if the stress is bigger than the one given by the symmetric one, I'm going to use the other part of the annulus, okay? And as I say, this is well defined because of the previous result. And now this height is going to be between 0 and 1, and cannot be 1 because 1 means that all the maximum are in the north pole. And the only case that can happen is in the topological list, okay? So this is the idea, right? The idea more or less is try to do something like that. I have my solution. My domain is between these two boundary components. This is the annular solution, okay? And I have the level set, okay? And I have graph of my U. And I have my model solution. And I'm going to take the model solution such that the maximum are going to be the same as the maximum of U, okay? And I'm going to compare, for example, with this, with this boundary component, and say that the Newman condition is the same, both. I can I can do that because I have this one parameter family in my rotationally symmetric solution. And what I'm going to do to compare is this sub-annulus here with this one. So the first thing that I'm going to do is the model solution. I can parameterize the height, the height, okay, using this chi function, using the implicit function theorem. That's what I'm going to do. Using now this correspondent, I'm going to transplantate the rotationally symmetric solution to this domain, and then compare the original solution with the transplantation of the rotationally symmetric solution to this part of the domain. The way to, yeah, tell me. Sorry, any question? No, it's okay? Okay, continue. So, the idea. So, I have solution in some domain or domain, whatever. I have the expected critical height, that this guy that is unique, it's well determined, is equal to R. I'm going to take the rotationally symmetric solution with the same value of the maximum, and then what I'm going to define is function here, okay? So some value U, and this one is the one given by the rotationally symmetric solution with the parameter given by this R, okay? What I'm going to use is to use the implicit function theorem in order to find two functions, because I have two branches. I have to recall that I have two branches, one here and one here, okay? In order to parameterize the whole thing, okay? And I'm going to use that in order to translate my solution. So given a point in my domain, I'm going to define this function that is now in the domain of parameter of the rotationally symmetric solution, okay? So this is the value of the function, and this is the chi. So what does it mean? So look here. So if I take a point, okay, a value of U, so that goes to some value here, and they give me a value here. And here, I'm going to, this is, say, here, chi of P, say this is P. I'm going to define U of R of this guy, okay? This is what I'm going to define. Well, more or less, what I'm going to define explicitly is using that function, what is the value of the gradient, okay? What is the value of the gradient? That's how to define this pseudo-radial function. This is, I didn't invent anything. This is everything contained in the paper of Agostiniani, Lorenzo, and Stefano. But we translate everything in our situation, okay? And the theorem is this gradient estimate. This is where everything is contained, more or less. That if you are able to prove this, so the rest are computation, but more or less are not so complicated. So the theorem say that the following. Once that we construct this pseudo-radial function, we're going to compute with the gradient, and we are able to compare the gradient of my solution with the gradient of the model solution. This gradient is explicit, so I can compute everything that I want to. So that's the good thing. And the idea is to use the maximum principle. How to use the maximum principle in a very clever way is the following. So we are going to take the difference, these both functions, and I'm going to multiply by some positive function that depend on the pseudo-radial function. And chosen appropriately this function here, so you are able to prove that this guy satisfies an elliptic equation, an elliptic inequality. Then you apply the maximum principle, and then you say what you see that if it's less or equal at the boundary, have to be less or equal at the interior. Okay, this is what we say here, and then that's the whole idea. The whole point is to prove that this guy satisfies an elliptic inequality. That's the whole point. These are many computation, but it's not complicated. But you have to do many computation, but it's not complicated. The idea is to find this beta. Since this is a function that depends on the pseudo-Radial function, in order to get rid of the bad term when you do the Laplacian of this guy in by brute force, in order to take away the bad term, what you see that this beta has to satisfy some ODE that you can solve. That's the whole idea. And then apply my principle. Okay. So now that you can compare your solution, the gradient of your solution with the gradient of the model solution, that's very nice, because now you can prove two things that are important for us. One is a Carvajal estimate for each boundary component, depending on the expected critical height, okay, depending on this. So this what it tells you is, suppose that you have a solution and you compare, this is U max, and this is the gradient of your solution, okay? You have one of those solutions. Okay, so this is in the model solution, okay? This is the equator. Say the height, the maximum, say, is here. So when you see this picture, this is what you really see, okay? This is U max, and this is the gradient here, okay? So what this equation tell you is that if your solution, your half of your solution, okay? Say, let's do, no, I want to do this. This is the maximum, okay? Say you are comparing this part here. This is gradient of U, okay? Okay, here, okay. So what this theorem tell you is the following, using the gradient estimate that we had before, is that suppose that you have a subannulus here, okay? And then you associated a unique rotationally symmetric subannulus that is this one, okay? Then the Carvajal at any point here have to be bigger or equal than the Carvajal of this boundary component that is this one. That's what it's saying, okay? Depending on where you are, if you are in this subannulus or the other one, okay? That is what it's saying. So you can compare the Carvajal of this guy in terms of the Carvajal of this one. That's that will say the first result. And the idea here is to use the gradient estimate and the Taylor expansion of the boundary, of the Carvajal along the boundary. It's not complicated. The only thing is to use this property here. And the second one is a length estimate. So you can compare the length annulus. You are comparing. So you are, say, in this subannulus here. So there is a way to compare the length of this guy with the length of this in terms of the length of the same geometric thing in the model solution, in the rotationally symmetric solution, okay? So this is done using a vector field, a good vector field on my domain. And then using the divergence theorem. So the idea here is the divergence theorem and a good vector field, and here is a Taylor's expansion of the boundary. Okay, now the theorem. So we can prove this theorem. So suppose that you have an annular domain, okay, of this equation, such that the Newman condition is locally constant along each boundary component, and also has a infinite many maximum point. Then this guy have to be equal to some model solution, okay? So, okay, condition here, as I explained before, what it gives you is the following, right? Is that you have your domain, 1, 2, you have an infinite number, so you have at least one analytic closed curve and probably some maximum, but now are isolated, okay? So this is the set of maximum points. Then I have two different sub-annulus, right? Say this one. The first thing is that, okay, I'm going to compute the tau for both of them, the stress function. What I have is that for each boundary component, I have two boundary components, okay? So what I know is I have a curvature estimate for each boundary component, right? But a curvature estimate tell you, using Blaschke's theorem, is that you have a length estimate. Have to be the length, because the curvature is bigger or equal than the one of the rotational example, the length have to be less or equal. So, and this is the length of the rotational example, depending where, if the stress is bigger than tau 0 or smaller than tau 0, depending where you are, okay? And now we use the length estimate that relate the length of the maximum and the length of the boundary, of each boundary component. Then what it tells you is that this is the estimate that we had before, the length estimate, with this one, tell you that the length of the maximum point, this is in the sphere, because it's easy for me to do it here, right? The length of this curve is less, you can see here, less or equal than 2 pi, right? Because R is between 0 and 1. This is equal to 9 to pi. So it's something from curve, closed curve, simply connected curve, convex curve in the sphere, that is the length is less or equal than 2 pi, either is strictly contained in a hemisphere or is an equator. So under this situation, you have two cases. If, in the first case, if it's contained in a hemisphere, then one of the two sub-annulus is contained in a hemisphere. Then you can use the moving plane method and prove that that hemisphere have to be rotationally symmetric, and by analyticity have to be everything rotationally symmetric. And if it's an equator, so the Cauchy-Kovalevskaya theorem tells you have to be the rotationally symmetric solution. So that's the thing. I have 5 minutes. So this is the theorem how to prove the rotational symmetry when you have an infinite number of critical points. So I would like to show you how to pass this to free boundary minimal surface, but I don't have time to explain the whole thing because are too many things. The thing is that let's focus only on free boundary minimal surface in the ball, assuming that both boundary components, suppose I have an annulus, and both boundary components are in the ball, okay? That's the one that I'm going to assume. This is more general, but it's not important. So the thing is that what I want to classify now, suppose that I'm in the ball and I want free boundary minimal surface, which are of annular type embedded, okay? Are of this type. So the model solution for these guys, we know, are the catenoids, okay? These are the, oops. So I would like to say that when I can say that solution to the problem free boundary minimal annulus are catenoids, okay? So, okay, I'm going to describe all the catenoids, I mean the axially symmetric catenoid, and I can describe it in this way. So with this parameterization, I can compute explicitly the normal, that is this one, and I can compute the support function. The support function is nothing but the product of the position vector of the normal, and the support function is given by this expression. As you can see, this is the expression of the solution that we had before, okay? So this guy satisfies this equation, that is the one that we had before. And the parameter that we had analytically before, we know that this parameter omega is nothing but the translation, okay? And this other parameter is the scaling of the catenoid. This is geometrically how you see the parameters in the previous you can solve it as we did, but geometrically is more clear in this way. So these are my model catenoids, and see from here is that a model catenoid gives you a model solution analytically. Okay, and then the model catenoids that are this is for some value R, and this is the critical catenoid, that is the one that is symmetric. Okay, now you have the plane of symmetry here, and correspond to the solution in my PDE setting where that is symmetric. So how to relate these two problems is that using this is older, but it's well stated in this paper of Travaswan, that tell you that if you have a minimal surface, such that the Gauss map is a global differ onto the image, then the support function, that is this one, is solution to this equation, and u equal to 0 means there is free boundary along the boundary. Okay, this is the free boundary condition, and this is the radius of the sphere where it's contained. Okay. So this theorem give you a relation between both. So using that relationship and our previous theorem, we can prove this theorem, but say probably the corollary is more understandable. So suppose that you have an embedded free boundary minimal annulus in the ball, okay, and the support function has infinitely many critical points. Observe that I wake the condition. I don't say maximum, I say critical points on, because in this situation we're able to prove that infinitely many critical points imply that these critical points are maximum points. But right now here I only need critical points that are way less than asking for maximum. Okay. Then the surface, the free boundary surface, has to be the critical catenoid. And the idea is very fast. Is the following. The first thing that you have to prove is that the Gauss map is a global differ onto the image. Okay, that is done using this point. The first thing that an embedded minimal annulus with free boundaries doesn't have umbilic point. Okay, umbilic point means that the curvature is 0. The Gaussian curvature is 0. Okay, this is using the Poincaré-Hopf index theorem. This is pretty easy. So since the curvature is never 0 because don't have umbilic point, the Gauss map, the differential of the Gauss map is never 0, then it's a local differ. Okay. Also using this condition implies that each boundary component in the sphere is convex as a curve in the sphere. Okay. Because the geodesic curvature in the sphere is equal to the square of the minus the curvature. You observe that the curvature is negative the Gaussian curvature is negative, right? In a minimal surface. So that tells you that the image of the boundary of your surface by the Gauss map is also convex in the sphere. Then convexity of the boundary and local differ, a simple topological argument, implies that the normal is a global differ between the minimal annulus and the Gauss image. Okay, that allows you to use the theorem of Swan that I said before, and take the support function and translate it to a domain, to another domain in the sphere. Okay. And now the second thing is to prove that the point of the support function implies that are maximum point. Okay. And the idea here is the following: a critical point of the support function is when the normal is plus or minus the projection. Okay. So that implies that you have a curve of critical point. The image by the projection and the Gauss map is exactly the same. Okay, these are the curve of critical point, and the image in the sphere is exactly the same. But observe that the normal takes the upper component and the lower component into the upper component. But the projection map, that is one, take the upper component in the upper component and the lower component in the lower component. So that'll tell you that there is no other critical point. All the critical points are this one. And then the only possibility is that there are maximum, because at least you have one maximum have to be here. So this proof. And then once that you have that, what you have proved with these two theorems or lemmas or whatever, is that when you transport the support function to this to the Gauss image, is a solution to the overdetermined problem given by u plus 2u equal to 0 in some domain, annular domain. Oops, sorry. In some annular domain in S2, u equal to 0, but this is the free boundary condition. Free boundary. And also the gradient is equal to 1, or actually in the case of the free boundary in the ball, this is 1, okay, plus the number of maximum point is infinite. Then it's rotational. But the only rotational minimal free boundary minimal surface are the plane or the critical catenoid. Then have to be the critical catenoid because the topology is the one of the angle. So that's how to relate both theorems. I think that's everything. Thank you.
Thank you, Jose, for your talk. We have time for questions now. So if you have a question, please ask it in the chat or simply unmute yourself and ask the question.
Can you say something about why the existence of non-symmetric examples doesn't go through?
Okay. Yeah. Well, doesn't go through. I don't know. That's what I would like to know. But okay. So you can try to. Yeah. The important point is the following. Okay. You can try to do a bifurcation argument. That's the whole idea in the paper of Agostiniani. Even Paul and collaborators have some kind of bifurcation argument for this equation in the sphere. Sorry. This equation in the sphere. But the problem is that I want to do bifurcation of this equation, but maintaining the two, maintaining the eigenvalue, okay? Normally, when you do bifurcation of annular solution, annular domains in the sphere, so you change the eigenvalue, you change this one. But if you change this one, when you construct back, it's not a minimal surface anymore. That's the whole problem. That's why it doesn't go through, or I don't know how to go through. So, but if you can do, and so you are in the sphere, okay, you have this rotationally symmetric solution, let's say one boundary here, one boundary here, okay, and you try to do bifurcation here of this equation, but maintaining the two, okay. So what you want is something like that, right? But in this new domain, you need that the new solution satisfy this equation. You cannot change the eigenvalue. That's the whole problem. It's clear what I said?
Yeah, thank you.
Okay, so if you can solve this, I would like to see it. So this is the thing. So do bifurcation, maintaining the two.
Thank you. Anyone else wants to ask a question or comment?
Maybe just a quick question. So I think at the very beginning you said when you were explaining the theorem, you said that for simplicity you take two boundary component, but it seems that this model solution. So do you have anything when you have multi-connected, more than one?
Is that, I mean, I can construct with more than two boundary components. That even I think that I don't think that you can construct a solution with more than 4 boundary components. That even three, I don't see how to do it. That I think that the most that you can do are 2. I cannot. You can do the argument because the argument don't depend. They depend at the end, only at the end, that you have 2 boundary components. But even in general, I think that you can construct a solution with more than 2 boundary components for this equation. I mean, for this equation, okay? Because this equation has a relation with the minimal surface. Because you say, okay, how to do it in some sense. So since it has to do with minimal surface, I should be able to find like a free boundary minimal surface with 3 boundary components. But the thing is that once that, if I assume that I assume that they have 3 boundary components, for sure, I will have umbilic points. in my meaningful surface. That means that the Gauss map is no longer a local difference at that point. So I cannot transplantate the support function. So this is what I explain here. So I suspect that probably for this equation, I can construct overdetermined solution with more than 3 boundary components. I don't think so, but I don't know how to prove it. I will let, but I don't know. And the geometric idea why not is because if that were possible, I were able to construct something like this, more or less. But this guy in the interior or along the boundary, has some kind of point P, where K of P, the Gaussian curvature, is 0. And this tells you that the determinant of the normal is 0. But this tells you that the normal is not a local difference. So it's going to be a double cover.
Thank you.
But I don't know how to prove it. I don't know how to prove it. But this is my idea. I think it's not possible.
So thank you very much. Anyone else wants to say something? If not, we should thank the speaker again. Thank you very much.
Thank you.
We will reconvene next week with a talk by Panagiotis Polymerakis, who will speak about large Steklov eigenvalues under geometric constraints. Thank you very much.